Okay, this is going to be my last video. I'll try and keep it short. I'm going to talk a little bit about stability. So we're talking about a differential equation f prime is equal to AF. So f is this vector valued function f of t, and we're just going to do the 2 by 2 case. A is a 2 by 2 matrix. And I talked last time about stability, and the issue is the following. You have this solution right here, the constant solution f of t is simply the 0 vector, just sits right there. That's a solution. And so now what we do is we deform the solution out a little bit and see what happens. It gets onto some new solution, which is on some trajectory, and the question is, do you move away from 0 or not? And I want to make this a little bit more precise. So here's the definition. The 0 vector, the constant solution, is, the first definition is stable. Stable. If the new solution stays close to 0 for all time. So it doesn't have to go back to 0, but it can't go far away. And the other definition is it's said to be asymptotically stable. What that means is that the new solution goes back to 0, but it doesn't really go back to 0. It goes back to 0 asymptotically. And what that means is, I'll draw this on the next slide a little bit bigger, but what it means is that as t goes to infinity, you get closer and closer to 0, but you don't actually get to 0 in any finite time. Well, let me do this two sort of defining examples. Let's do asymptotically stable first. The key example of this is this very elementary one where you just have -1 on the diagonal. We talked about this in class. The trajectories all look like straight lines, or rays. Oops, that one missed. Where all of the arrows are pointing in towards the origin. And this is asymptotically stable because if you take any solution, you take the 0 solution and deform it out somewhere, I'll say all the way out to here, say, then what happens as t goes to infinity is it goes back along this curve towards 0. But it never actually gets to 0. What happens is as t goes to infinity, f of t goes to 0, but it never actually reaches it. And it can't reach 0. That bears thinking about for a second. It can't reach 0 for the following reason. Let me draw a picture over here. So remember, 0 is a solution. And there are these other solutions, whatever they are. There's curves. And one of these curves that goes towards 0, well, if it actually hit 0, that would be a contradiction to the business that these curves can't intersect. This curve here and the curve 0, which isn't much of a curve, but it counts, would be intersecting, and that's not allowed. And so this can't happen, and that's why you never actually reach 0. Okay. Well, let's be even more concrete about it. Suppose you deformed out to the point. Suppose you deformed out to the point 1/10 0. That's on the x-axis here. Well, the solutions through this are given by f of t is equal to some constant times e to the minus t times 1, 0, which is to say a constant e to the minus t, comma, 0. And as t goes to infinity, what does this do? Limit as t goes to infinity. Well, I shouldn't say the limit. Let me just say as t goes to infinity, this is going towards 0 because this e to the minus t is going asymptotically to 0, but it's never actually reaching it. Well, okay, let's look next at an example which is stable, but not asymptotically stable. So to say that it's stable means that the new solution stays near 0, but if it's not asymptotically stable, it doesn't go to 0. So how can that be? How can it stay near it but not actually approach it? Well, if the only way, there's basically only one way, and that's because the solutions are circles. So the standard example is this matrix here. And we know that the solutions to this, the trajectories, are a bunch of concentric circles. And if you start at 0 and deform out a little ways, the new solution that you get on is this circle. And you go around and around that circle forever. You stay near 0, but you don't actually approach it. So that's the notion of stability. Okay, well, I'm not going to try and march through all of the cases systematically. You can see that in the book, but let's do some of them. So one of the easiest ones is the case where you have two eigenvalues, lambda 1 and lambda 2, and we've already seen if they're opposite signs. So let's say lambda 1 is less than 0 and that's less than lambda 2. We saw that the trajectories look like this, and that's definitely unstable. And another possibility is that they're both positive, in which case I did an example last time in class where the trajectories look like this. Is a typical example. And the arrows are pointing out. So, again, it's unstable. And if you had the same thing where lambda 1 and lambda 2 are less than 0, well, it's the same picture, except you turn the arrows the other way. So the trajectories look the same, except the arrows are pointing in. And this kind of thing is asymptotically stable. So let's take a gander here. If they're opposite signs, it's definitely unstable. If they're positive, it's unstable. The only way it can be stable is if both, or asymptotically stable, is if both of the eigenvalues are negative. And that's more or less the what happens in general. Okay, well, I'm not going to try and march through all of the cases systematically. You can see that in the book, but let's do some of them. So one of the easiest ones is the case where you have two eigenvalues, lambda 1 and lambda 2, and we've already seen if they're opposite signs. So let's say lambda 1 is less than 0 and that's less than lambda 2. We saw that the trajectories look like this, and that's definitely unstable. And another possibility is that they're both positive, in which case I did an example last time in class where the trajectories look like this. Here's a typical example. And the arrows are pointing out. So, again, it's unstable. And if you had the same thing where lambda 1 and lambda 2 are less than 0, well, it's the same picture, except you turn the arrows the other way. So the trajectories look the same, except the arrows are pointing in. And this kind of thing is asymptotically stable. So let's take a gander here. If they're opposite signs, it's definitely unstable. If they're positive, it's unstable. The only way it can be stable is if both, or asymptotically stable, is if both of the eigenvalues are negative. And that's more or less the what happens in general. Let's look at the complex eigenvalue case. So I've done some of these. Let's do an example. A1 minus 1a. This has characteristic polynomial a minus lambda squared plus 1 is equal to 0, which says that a minus lambda squared is equal to minus 1, or a minus lambda is equal to plus or minus I, which says that lambda is equal to a plus or minus I. So the a is fixed, and you're just changing the sign on the I, of course. And I mentioned that it's the sign of a that matters. Well, we already saw if a is equal to 0, so you're just talking about 0, 1, minus 1, 0. These are the circles. And this is the one case which is actually stable, but not asymptotically stable. If a is positive, that's where you get these spirals going out. And if a is negative, that's where you get these spirals, except the arrows pointing in. And if the arrow's pointing out, it's clearly unstable. And if the arrow's pointing in, it's clearly stable. So how can it be stable or asymptotically stable? We're just looking at these eigenvalues. If this a is 0, or I forgot to write the 0 here. If the a is 0 or negative, then you get stability, and if it's positive, it's unstable. So that basically gives us enough examples to say what's happening. So here's the final result about all of this. So we're looking at the differential equation a prime is equal to a f, and I'm just talking about the 2 by 2 case, although I'll say a word about the general case. And we're talking about the 0 solution, whether it's stable or not. So the first thing is that 0 is asymptotically stable if and only if the real part of lambda 1 is less than 0. And if there are two eigenvalues, the real part of lambda 2 has to be 0, less than 0 also. This means the real part. So if it's real, if the eigenvalues are real, it just means lambda 1 and possibly lambda 2 are negative. If you have complex eigenvalues, they're a plus or minus ib, and it says that a has to be less than 0. And the condition for stability, it's just slightly weaker than this. It's if and only if the real part of lambda 1 is less than or equal to 0. And similarly for lambda 2, if there are two eigenvalues. So again, if they're real, it says lambda 1 and lambda 2 are less than or equal to 0. And if they're imaginary, then lambda 1 and lambda 2 have to be just plus or minus I times b. And so notice that the solution is stable, but not asymptotically stable, exactly in the case when you're getting a 0 here, when the real part of the lambda i's of lambda 1 is equal to 0. And that's where you're getting these circles or ellipses. Well, let me say just one last thing. I've just written it out on the slide. What I was just talking about was the equation f prime is equal to af, and what I'm pointing out here is that if you change those 2's to n's, it's essentially the same result holds. Asymptotically stable holds if and only if all of the eigenvalues have real part less than 0, and stable you allow real part less than or equal to 0. And, well, I won't say any more about that, but I'll just point you to theorems 9.15 and 9.20 in the book.